So yeah, so my slides are brief, but I want to tell you a little bit about the kinds of quantum computing, quantum information things that my group is doing here at MSU. And
yeah, that one there, yeah.
So our group is the Laboratory for Hybrid Quantum Systems in the physics department. If you want to check out our website, if at any point in time in these 3 slides you get absolutely bored with what I'm saying, just check out our website. So the 2 things I want to highlight that are really the most directly connected to quantum computing are our development of hybrid quantum systems to develop new qubit candidates, specifically the one that I work on with my partner in crime, Mark Dickman. Namely these electron motional states on the surface of liquid helium. And the second part that I want to tell you about is our effort to work with superconducting qubit architecture. So these are the kinds of systems that were originally developed at Yale, and that Google and I have formed the platform for what Google and IBM do. And our broad goal, so maybe I should also start by saying, maybe everybody should do this, that I think that we, like Mark, Google, IBM, possibly Intel, are close to quantum supremacy. I think this will happen within the next 1.5 or 2 years. I think that we're right on the cusp. Bristlecone, the 72.
Can you define quantum supremacy a little more precisely?
Yeah, so that's a good question. So I'll use the general definition. And it's also, I think, the most forgiving definition, which is that we will be able to work with quantum systems that are impossible to simulate on a classical supercomputer. So if you, at least some aspect of that quantum system. And so John Martinez is always a little bit, that's the answer that he gives, so that's partly why I'm giving it, but he's always, this is something that's a little bit ill-defined, and it depends a little bit on.
If I measure an energy level in a many-body system that theorists cannot compute,
yeah, so
then that's quantum supremacy by your definition.
Right, by definition, right,
so,
yeah.
So we're there already.
Right, and by that definition we're there already, but his definition would exclude that. I would say that
okay.
He would say that if you can, he wants 72, or however many qubits that he can control individually and perform 1 and 2 qubit operations on, and to simulate a system like that would be possible. But that's a good point. Like I say, the Bristlecone processor, which is currently under test, may be the one that demonstrates this. But our goal in my group, in addition to demonstrating so Steve brought up a good point. We live in a situation where, in the imminent future, I would say right now actually, we have intermediate scale noisy quantum computers, and that means that things like how to control noise, how to eliminate decoherence are really important questions. And those are the kinds of questions that my group is ultimately interested in. And we think that there's potential for this electrons on helium approach to not only tell us about those kinds of effects, decoherence and noise, but also present us with maybe something that isn't a Babbage machine, or maybe it is, but I think we do have to try these out. And so the goals are new qubit architectures, developing new readout electronics and protocols, and then developing resonator couplings that allow us to store quantum information and maybe even control it. So I'll say a little bit about that. So I'll start with the superconducting qubit thing because that's more conventional quantum computing. So we work with a particular realization of this known as the 3D transmon. So we have inside of this aluminum box, which is a microwave cavity, a small squid loop. So this is just 2 pieces of aluminum that are separated from each other by an aluminum oxide layer, and that looks like this. It has a 2-level structure that functions as a qubit, and it's tunable. And what we can do is we can apply microwave pulses that allow us to control the probability of being either in the ground state or the first excited state of this system, and essentially move a vector on the Bloch sphere to any position that we want. And so what we're trying to do that's relatively novel with this system, stand over here, is to couple this to resonators. So not just the resonator that is the microwave cavity that this thing lives in, but actually acoustic resonators. So this is something that a lot of people are working on right now, and it's actually even developed its own acronym and name. It's called Circuit Quantum Acoustodynamics. And what we do is we couple this kind of qubit to an elastic wave on chip that wiggles around at the same frequency as the qubit. And building resonance structures out of those kinds of surface acoustic wave devices is very much in vogue right now. we're trying to do it too. But this is really nice because you can use these resonance structures, which have extremely long lifetimes, to store quantum information, to create non-classical states of elastic motion, and to hopefully be able to do on-chip interrogation of qubits wherever you want.
So those phonons are at that micro
Yeah,
scale?
yeah. So we transduce a microwave photon into an elastic wave on the surface of a piezoelectric crystal. And one of the really fun things about this is, microwaves are like this big, and they oscillate at, let's say, 5 gigahertz. And what we can do, but the qubit is like, 2 microns. And so being able to do this, turning it into sound or into an elastic wave, allows us to shrink the wavelength of that excitation down to micron scale. So one of the fun things is one can simulate circuit quantum electrodynamics far outside of the dipole approximation with this kind of approach. Depending on which theorist I ask, I get a response of either that's really interesting or nothing will change, which makes me interested. But one thing I'll say is that we do this work in collaboration with Cater Murch at Washington University in St. Louis, and he's an expert in studying the time trajectory of quantum systems that you can control and coupling them to baths, and so yeah, he's another partner in crime. So that's one of the things that we're doing. And the second one is this development of a new qubit candidate. So trying to figure out systems that might behave as better qubits, both in terms of their decoherence and in terms of their scalability. And the one that we want to use is this single electron floating in vacuum above liquid helium. So we can trap these. There's been there's a handful of groups around the world that work on this. There's us. There's a group at the University of Chicago. There's a group at Princeton. There's one group in Japan. There's a group in Moscow. And there's a collaboration with Sandia National Labs. And the University of Chicago group recently demonstrated a really beautiful single electron motional control. Well, they've just demonstrated the existence of a motional state that could potentially one day be a qubit. And so we're working in that direction as well. And so we fabricate and design single electron devices for hopefully creating a qubit out of this state. And this is a collaboration that I have strongly with Mark Dickman. He and Phil Platzman were the original people that proposed using this system for quantum computation, either the vertical motion of this. So I want you to imagine, it's really an electron bouncing around on the surface of liquid helium. And it's a qubit system that's somewhere between the trapped ion systems that the companies like IonQ and Chris Monroe use, and the superconducting qubit systems that Google and IBM work with. And the beautiful thing about this system is the helium really separates you from charge noise that exists on the surface of any substrate. And so this is a really wonderful, at very least, an amazing test bed for studying noise in quantum systems and their decoherence effects, and possibly for building a large-scale quantum computer. And so that's what we do. We're developing single electron devices and sensors and trying to do single electron control with this. This is a picture of the systems that we use in the lab for doing this, and we get a whole bunch of support from a variety of people. The National Science Foundation, we have a nice collaboration with Sandia National Labs, and we've actually had private interest in working on this system. So I should mention the MSU Cowan Endowment, which is really wonderfully supportive of our department and my group in particular. But ask me questions, sorry.
Excellent. No, good.